Hello everyone. Today I'm going to be presenting our work on multi-level attention aggregation for aesthetic face relighting. Face relighting estimates the illumination cast on portrait images by a light source varying in both position and intensity. An example video can be seen below. The shadow cast on the face varies depending on the direction of the light and its intensity. The goal is to render aesthetic relit images with accurate shadows. Broadly, most prior work can be categorized into three different approaches. One approach estimates the albedo, surface normal, and shading map from an input image to subsequently estimate the relit image. Another approach is to learn a model to directly translate from the input image to the relit image. Some have explored using the lighting in a reference image to relight a source image. An important aspect of relighting is to accurately estimate shadows. Towards this end, methods have looked at estimating a shadow mask and weighting it appropriately with the input image, or using geometric principles to determine the direction of shadows cast on an image. While these methods work well, there are a few limitations. Estimating intrinsics can lead to cascaded errors downstream. Most methods are trained on synthetic images, but to achieve generalization, they add pseudo-real ground truth images. So while they achieve generalization, the rendered images are not always accurate and photorealistic. But obtaining real image datasets for face relighting is very difficult and expensive, as this requires an OLAT lighting rig as seen here. Each light is lit one at a time in a sequential manner to capture input relit image pairs. We try to overcome some of the limitations of prior work. We try to explore if the synthetic data alone is enough and sufficient for generalization to real images. Towards this end, we created a synthetic OLAT lighting rig in Blender software and used a novel dataset composition strategy to create the training dataset. We use a two-stage training pipeline to achieve unsupervised adaptation from synthetic to real images. As mentioned, we created a synthetic OLAT lighting rig in Blender and generated training dataset using synthetic 3D human models. A training dataset has photorealistic and accurate shadows. We argue that it's easier to learn the foreground subject than the relationship between the face pose, light direction, and shadows. Thus, we use a novel dataset composition strategy to create our training dataset. We used just 8 3D human models and generated 3000 lighting variations for each model. The light source position was densely varied along a unit sphere. We densely varied the light source intensity too. We use multiple augmentations such as varying the ambient light intensity, the relative orientations of the 3D model with respect to the camera, or even the position of the 3D model with respect to the camera. Some of the variations are shown in the slide here. Although the training dataset was just 21,000 images, it is a rich and diverse dataset that captured most of the variations encountered in face relighting. We used a two-stage training pipeline to train our model. In the first stage, a residual convolution autoencoder was trained. In stage 2, a GAN was trained where the network from stage 1 was used as the generator. This network architecture enabled us to achieve unsupervised domain adaptation from synthetic to real images. We use a standard ResNet architecture in the encoder and decoder for stage 1 training. At each layer of the skip connection, we used a multi-head attention module. Capturing attention features at high resolutions allowed the network to learn fine-grained facial and shadow details that get lost at lower resolutions. The 4D light vector of its position and intensity was converted to a 10-dimensional SH coordinate and fed to the lighting network. The light features were combined with image features and passed to a decoder which learned the relationship between them. The stage 1 network was used as a generator in the GRAND framework for training the stage 2 network. The discriminator architecture was designed to be same as that of the encoder from stage 1. For stage 1 training, the losses were computed at both global and local scales to ensure that the network rendered accurate and realistic relit images. In the stage 2 training, adversarial loss was additionally used. Through adversarial training, the generator network was able to generalize from synthetic to real images in an unsupervised manner. The discriminator is only required during training, and at inference, the output from the generator or the stage 1 network is the estimated relit image. We evaluated the performance of the model on two very challenging real image test datasets. The real image datasets were designed to have out of training light source positions and intensities. We compared the performance of our model against three most relevant prior works which have been trained on real images. Despite our model being trained only on synthetic data, we observed that we significantly outperformed the prior works on these challenging real image datasets. Qualitative results from our model can be seen on this slide. We can observe that the stage 2 model is able to estimate a more photorealistic relit image which is very close to the ground truth image. Both stage 1 and stage 2 models are able to accurately render sharp shadows and estimate a photorealistic relit image. We can see from qualitative comparisons with prior work that our model is able to estimate a more accurate and photorealistic relit image irrespective of the ambient lighting intensity or the facial structure. We see that compared to these prior works, the shadows are more sharp and they blend in a more natural manner in the face. We are also able to achieve very good generalization to out of training light source position. Though our model has been trained only on light source positions contained within a unit sphere, we tested it on light source positions at x equal to 2 and x equal to 3, or similarly for y and z. Here we show the results for varying x, y and z respectively at each row. We varied the light source position along x, y and z while retaining the other two values to be the same. As the light goes farther, the effect of point light source reduces and shadows become less dense and the face is more uniformly lit. We see that our model is able to capture this behavior. In conclusion, we showed that a novel dataset composition strategy and a novel network architecture enabled our model to achieve very good performance on challenging real image test datasets despite being trained only on synthetic data. Attention modules at higher resolution captured fine-grained facial and shadow details which get lost at lower resolutions. The relit images estimated by our model are more accurate and photorealistic as seen from the quantitative and qualitative results. Thank you.